In this video, we will work through several examples of converting between mass and volume and mass and volumetric flow rates by considering the density or specific volume for the component. We will also consider a constricting gas flow through a cone-shaped pipe and finish with a basic example of determining the fluid velocity through a pipe. In this first example, we are asked to determine the volume of a known amount of carbon tetrachloride in centimeters cubed if we know the density in grams per centimeters cubed. Now, the first thing I want to take note of is the fact that I see a slight discrepancy between some of the units. While we can obtain centimeters cubed from our density, as you can see there, the mass is given in pounds, whereas in the density, the mass unit is given as grams. So the first thing we will need to ensure is that we convert our mass into grams. So the way we do that is by writing down our unit conversion. So our unit conversion factor would be 1,000 grams is equal to 2.205 pounds. And then we have our mass, and that will be equal to 6.2 pounds, but we wish to obtain these in grams so that we have consistency with our density units. So we will multiply by 1,000 divided by 2.205. Why? Because 1,000 grams per 2.205 pounds. And that gives us, if we cancel out our units of pounds, we end up with 2,811.79 grams. Now, the volume then is simply given as volume is equal to mass divided by density. Now, I may choose to present this as symbols. V is equal to M divided by rho. And that is then equal to 2811.79 divided by 1.595. And here we could just write our grams and our grams per centimeters cubed. Our grams will cancel out. Our centimeter, well, that's 1 divided by 1 over centimeters cubed. So 1 divided by 1 over centimeters cubed. That's same as 1 times by centimeters cubed divided by 1. Hence, the units end up with centimeters cubed. So now if we do the numerical calculation, we obtain 1762.9 centimeters cubed. In this question, we were asked to determine the mass of a gas in kilograms when its volume is 0.015 meters cubed and its density is 1.2 pound per foot cubed. So first thing we'll need to do is ensure that we obtain a consistent unit. And the issue here is that we have our mass that we're trying to obtain in kilograms, our volume that we're given in meters cubed, and the density is in pounds per foot cubed. So we'd really like to get our density in the same units as our mass and our volume, namely kilograms and meters cubed. So the way that we'll do that is use our conversion factors. So we should note that 3.281 foot is equal to 1 meter. And we should also note that 1 kilogram is equal to 2.205 pounds. Then to convert our density, so our density is simply given as 1.2 pounds per foot cubed. So therefore we'll have to multiply by, and we want to cancel out our foot cubed and replace it with meters. So we want to get meters cubed. So we know that 1 meter cubed, well, that's 3.281 feet all cubed. And then we'll multiply this also because our feet cubed, so the feet will cancel out with the feet. And
our mass we wish to obtain is kilograms, so 1 kilogram divided by 2.205 pounds. Now, doing this calculation, we obtain 19.22, and the pounds will cancel out, and we're left with kilograms per meter cubed. Okay, so now we have a consistent unit for our density. What's left to do is calculate our mass. And the equation we have that connects our mass to our volume with density is equal to mass divided by volume. So rearranging this equation for mass gives us mass is equal to density multiplied by volume. So that will give us a value of 0.015 meters cubed. Sorry, that's our volume there, that's V, multiplied by our density, which is 19.22 kilograms per meter cubed. And again, this is our density. So the order doesn't matter for our multiplication. Calculating our values and cancelling out our meters cubed gives us 0.288 kilograms. In this question, we're asked to determine the volume in foot cubed, given a known mass and our density in pounds per foot cubed. So again, our volume will be given by this relationship, rho is equal to m over v, and rearranging this, we will obtain v is equal to m divided by rho. Of course, before we actually plug in our values, we'll need to convert our mass into a consistent unit, because our mass must be in pounds to be able to use that density, and we wish to get it in feet cubed. And of course, we have that appropriate unit in our density. So note that 1 pound is equal to 0.454 kilograms. And now to convert our mass into pounds, our mass is equal to 215 kilograms multiplied by 1 pound divided by 0.454 kilograms. Kilograms cancel out, and we obtain a mass of 473.57 pounds. And now to calculate our volume by plugging into this equation here. Our mass is 473.57 pounds divided by our density, which is 845.7 pounds per foot cubed. Again, our pounds will cancel out, our foot cubed comes to the top, and we obtain 0.56 foot cubed. In this example, we're asked to determine the volumetric flow rate. The volumetric flow rate, V dot, from the mass flow rate, M dot, given the density 0.659 grams per centimeters cubed. So one thing you'll notice is that we have quite good consistency. We see grams and grams, we see centimeters cubed, and we see per second and seconds. So there's no conversion required for this question. We know that our mass flow rate, m dot, is equal to our volumetric flow rate multiplied by density. So we can rearrange this equation and obtain our volumetric flow rate is equal to our mass flow rate divided by our density. Now, plugging in our values of 6.59 grams per second divided by our density, which is 0.659 grams per centimeters cubed, our grams will cancel out, and we obtain 10 centimeters cubed per second. In this question, we were asked to determine the mass flow rate of our carbon tetrachloride once again, and if we are given the volumetric flow rate and the density. Now, one thing you'll note here is that we have consistency with our centimeters cubed in both our volumetric flow rate and our density. And the units of our mass flow rate, have a think about what those might end up to be. And once you've had a thought, you might have realized that our mass flow rate that we'll obtain will be in grams per minute. And since the question doesn't ask us for a particular unit for our mass flow rate, we can just assume that's correct. So our mass flow rate is given by our volumetric flow rate multiplied by our density. Our volumetric flow rate is, of course, 100 centimeters cubed per minute. Our density is 1.595 grams per centimeter cubed. Centimeter cubes cancel out, and we obtain 159.5 grams per minute. Now, we can also multiply this value into, we could obtain the units in grams per second if we wished. It's not asked in the question, but let's go ahead and do it. So the conversion factor between minutes and seconds is, well, 1 minute is equal to 60 seconds. So we're trying to get rid of our minutes, so 1 minute must come at the top. Divide by 60 seconds. Minutes will cancel out, of course, and we obtain a value of 2.66 grams per second. So we've converted between units. In this question, we're asked to consider a gas flowing through a cone-shaped pipe. And we're asked to compare the mass flow rates of the gas at the inlet and the outlet. Well, one thing we know is that from the law of conservation of mass, and intuitively we can determine this, is that the mass flow rate in, let's call it m dot I, must be equal to m dot O, or the mass flow rate out. So for the law of conservation of mass to be considered true in this case, we must make the inlet mass flow rate equal to the outlet mass flow rate. And then the question asks us two follow-up questions. Well, what would be the case if the density of the gas is constant? What about the volumetric flow rate at these 2 points? Well, if rho is constant, if rho is a constant, and it follows that V dot is equal to our mass flow rate divided by our density, well, this would be our flow rate, volumetric flow rate going in, and our volumetric flow rate coming out would be equal to our mass flow rate out divided by density. And what we can see is, because of the fact that the mass flow rate in is equal to the mass flow rate out, even the volumetric flow rates will be the same. We're also asked to consider a second case. What if the density decreases from the inlet to the outlet? Now comment on the volumetric flow rate. Well, what we'll consider here is that, again, the mass flow rate in will be equal to the mass flow rate out. So if mass flow rate in is equal to the mass flow rate out, well, in that case, if the density decreases from the inlet to the outlet, so density, as we move from our mass flow rate in to the mass flow rate out, what's happening is our density is decreasing. So now if we consider, the law of conservation of mass must remain true. Therefore, if we wish for the mass in to be mass out, to equal to the mass out, or the flow rates, then it follows that the volumetric flow rate coming out must increase. Now, why is that the case? Because rho v, our mass, is equal to rho v. So if our mass flow rate must remain constant and our density, if our density decreases, to ensure that our mass flow rate, so these are flow rates, to ensure that our mass flow rate stays constant, our volumetric flow rate must increase. In this question, we're asked to determine the velocity of a fluid, knowing its volumetric flow rate and the pipe diameter. So we're going to go and write down our velocity equation, which is, of course, our volumetric flow rate divided by our cross-sectional area. And we'll assume this is a constant cross-sectional area. And because the diameter is given, we'll assume it's circular. So the area of the pipe would be equal to pi d squared divided by 4. Now, we'll want to convert our 126 centimeters into meters so that we have consistency with our volumetric flow rate. So just to calculate that out, 0.01 meters is equal to 1 centimeter. So there's our conversion factor. So we'll try to couple this up with calculating our diameter squared. So pi multiplied by 126 centimeters multiplied by 0.01 meter divided by 1 centimeter. And now all of this is squared. Of course, our centimeters will cancel out. So this converts into 1.26 meters. And then, of course, we've got to divide through by our 4. And calculating that out, we'll get, of course, the units of meters squared as we anticipated, 1.247 meters squared. Then all that's left to do is calculate our velocity. Our velocity is our volumetric flow rate, which is 5 meters cubed per second, divided by 1.247 meter squared. And here you can see our meter squared cancels out with some of our meter cubed, and we're left with 5 meters per second divided by 1.247. That gives us a value of 4 meters per second.